Greetings and welcome to the Stellar. In the previous class, we discussed about three important thermodynamic equations. The first one was Antoine equation, in which we related the vapor pressure and temperature. So this was the equation where A, B, and C are the Antoine constants. All right. Whenever you'll be using, you'll be given to use this equation, they'll be giving you the units for Antoine equation, for pressure and temperature. So based on that, you have to substitute the values. All right. Then we move on to the next equation, which was the Clapeyron equation. So in the Clapeyron equation, we discussed the equation as dP by dt is equal to delta H by R delta V. Sorry, delta H by T delta. Delta H by T delta V. So this is the equation that relates the equilibrium pressure and temperature. All right, it relates the equilibrium pressure and temperature. Delta H is the enthalpy of vaporization, or basically the enthalpy of phase change, right? And delta V is the volume change as the phase changes, right? So as a special case of this equation, when we take an assumption that temperature is very, very less than critical temperature, and this assumption that delta V, which is Vg minus VL, is approximately Vg, which means VL is very small. It is negligible. All right, that is the second assumption that we take. And the third assumption that we take is that Vg follows ideal gas law. So on the basis of these three assumptions, we make it as we get the Clausius-Clapeyron equation from these three assumptions. All right. So the Clausius-Clapeyron equation states that ln P2S by P1S is equal to delta H by R times 1 upon T1 minus 1 upon T2, right? This is the Clausius-Clapeyron equation. This basically tells you the tells you the relation between saturation pressures at different temperatures, right? So that is very important. So in case if it is assumed that enthalpy of vaporization is constant, enthalpy of vaporization is constant, enthalpy of vaporization is constant between T1 and T2, then we can find the enthalpy of vaporization by relating the saturation pressures and saturation temperatures according to this equation. So this is one application that it finds. And the second application is that if you know vapor pressure at a given temperature, then you can find the vapor pressure at some other temperature. All right, considering enthalpy of vaporization is constant. All right. So this was what we discussed in the previous class. Now today we are going to start with a very important topic, and it is going to be continued for a very long time. So this is Carnot cycle. All right. Carnot cycle is actually the basis for second law of thermodynamics. All right. So we'll be discussing about Carnot cycle. We'll be discussing about the stages involved, steps involved in a Carnot cycle, and how is it applied to different conditions. All right. So we'll be discussing about this. And further, this cycle is going to be applicable in various other applications of thermodynamics. For example, in refrigeration, you'll be using Carnot cycle for a small part. Then even in heat pump, you at times use the Carnot cycle. So basically the fundamentals that you developed over here, they are going to be applicable in a lot of applications of thermodynamics. So it's going to be very important. All right. So before we start with the Carnot cycle, let me introduce you to the second law of thermodynamics. So far, we have discussed the first law, which states that heat added is stored as internal energy, or it is used to do some work, right? That was the first law of thermodynamics. And then the same law when applied to flow processes, we discussed that it is the law that governs energy balance within that particular flow process, right? That's what we discussed about firstly. Now, in the first law, if you remember, we discussed that heat is basically any form of energy. Heat and work both are the same. Both are forms of energy. Now, the difference that we said is that heat is the energy transferred because of temperature difference, and work is basically any energy transferred, which apart from the reason being temperature difference. All right. Other than temperature difference, if energy is transferred because of some other reasons, then that is work. All right. That energy transferred is work. That is what we discussed in the first law. But um, we did not discuss about the direction of energy transfer, right? There was one issue. So, for example, if a system over here, it has lower temperature and the system over here has higher temperature, then in that case, the law of energy balance would even satisfy if the heat is being transferred from lower temperature to higher temperature. Even there, energy balance can be possible, right? Energy balance explains that, okay, even temperature can be transferred, the heat can be transferred from lower temperature to higher temperature. But that's not what actually happens, right? So this phenomenon, why isn't the heat transferred from lower temperature to higher temperature? This phenomena is not explained by the first law. At the same time, the first law considers both heat and work as same, right? It doesn't have any qualitative, it doesn't keep in mind the qualitative difference between heat and work. So that is why we need another law which keeps all these things in mind. And then the combination of these two laws is going to help us formulate our thermodynamic systems. All right. So the second law basically states that all heat transferred cannot be converted to work. This is very important. Whatever heat, suppose if I have this as my system, and if I'm transferring some heat to the system, then all of this cannot be converted to work. This is one very important thing. Some of it will get dissipated. Some of this will get dissipated. It will get wasted. All right. So this is very important. Okay, so some of the heat will get dissipated to the surroundings. All of heat cannot be transferred. All right, so transformed to work. So this uh, is the second law of thermodynamics, and this is going to be very important. All right, this is going to be very important. This has a lot of significance. All right, so now we move on to something called a heat engine. So a heat engine is defined as a device that converts heat or thermal energy into mechanical energy, which can be used as work. All right. So any device which converts heat or thermal energy to mechanical energy is a heat engine. All right. That is defined as heat engine. So heat energy is converted into work. All right. But again, in the second law, it states that all heat cannot be converted to work. So some of it would get wasted too. All right. Some of it is going to get wasted. But heat engine is basically a thermodynamic heat engine which converts heat or thermal energy to work. All right. Now, thermodynamic cycle and heat engine, when we talk about every single thermodynamic system in a particular state, uh, which exists in a particular state, when a system takes through a series of different states and finally it is returned to its initial state, the thermodynamic cycle is said to have occurred. This we have discussed, right? From one state to other, the other state to the third to fourth, and then finally first. So this becomes a thermodynamic cycle, right? In this process, the system may perform work on its surroundings, for example, by moving a piston, thereby acting as a heat engine. All right. So as we discussed, that heat engine basically performs work by converting thermal energy into or heat energy into work. So that's what it can actually do. Heat energy can be used to can convert it into work. So that can be done. So in that case, if a system is performing a thermodynamic cycle, if a system is going through a thermodynamic cycle, then in that case, it can also work as a heat engine if it does some work on its parts. All right, keep this thing in mind. So now, when we talk about Carnot engine, so Carnot engine is basically a heat engine. A Carnot engine is a heat engine which is developed or which does work because of a thermodynamic cycle known as Carnot cycle. All right. So if a system is going through a passing through a series of states according to the Carnot cycle, then in that case, the system which the work that is going to be done, that work is actually going to be done by a Carnot engine. So in that case, the system would act as a Carnot engine. All right, the system would act as a Carnot engine. So remember, Carnot engine is an ideal and theoretical engine. All right, it is ideal in nature. Okay, so since it is ideal, so efficiency of Carnot engine is maximum. All right, efficiency of a Carnot engine is maximum. Okay, so if a particular engine claims its efficiency as something, and that efficiency you don't get from the Carnot engine, then in that case, or that particular efficiency is more than what you get from a Carnot engine, then in that case, that claim is wrong. Okay, so suppose if some manufacturer claims that the efficiency is 75% and the Carnot efficiency you're getting to be 60%, then in that case, this claim is going to be wrong. All right, this claim is going to be wrong. Okay, now let's understand what a Carnot cycle actually means. Okay, so consider this system. So in this system here, this is my piston cylinder arrangement. Over here in the center, I have a piston cylinder arrangement. This is a gas. All right, this is a gas over here. This is a high temperature reservoir, which is maintained at a high temperature. We'll be denoting high temperature as TH. And this is a low temperature reservoir, which is maintained at a low temperature. We'll be denoting this as TL. All right. So what will happen as these two come in contact with this gas? So what will happen? This gas is going to absorb some heat from the high temperature reservoir. All right. This gas is going to absorb some heat from this high temperature reservoir. When it absorbs some heat from this high temperature reservoir, it is going to do some work. All right. It is going to do some work. Then after some time, it is going to do further. It is going to do work. All right. And then let's say it is work is done on the system. So it is going to lose some of its heat to the low temperature reservoir. This is what is basically your Carnot cycle. All right. So the system absorbs heat from the high temperature reservoir and it loses some heat to the low temperature reservoir. All right. So in this process over here, when it absorbed heat from the high temperature reservoir, it did some work. And when it released heat to the low temperature reservoir, work was done on the system. So all together, whatever work is extracted throughout the condition, in that work is considered as the work output of the Carnot cycle. All right, the work output of the Carnot cycle. So we'll come to this once you understand what the Carnot cycle is, how it works, then we'll understand. All right. So Carnot cycle involves 4 steps: isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. All right. So let's say it starts from state A. So it isothermally expands to form to come to state B. So this is an isothermal expansion. All right. Then from state B, it adiabatically expands. All right. It adiabatically expands to come to state C. All right. Then it isothermally, it is compressed. All right. Isothermally, it is compressed. And then it is adiabatically again compressed. So finally, it completes the cycle and comes back to its state. Now, if you remember, we discussed the isothermal and the adiabatic process long back. And over there, we discussed that isotherm and adiabatic both have almost the same shape, right? So we can predict which curve, which one is an isotherm and which one is an adiabatic. So I'm going to explain that right now. So for an isotherm, if you remember, the equation of state was PV is equal to constant, right? And for an adiabatic system, the equation of state was PV to the power gamma is equal to constant, right? So now if we differentiate this, so we'll get PdV plus VdP is equal to 0. And from here, we'll get PV to the power gamma minus 1 dV plus V to the power gamma dP is equal to 0, right? So from here, I'm so sorry, P gamma PV to the power gamma minus 1 dV, right? Plus V to the power gamma dP equals to 0, right? So from here, when we get dP by dV, that is going to be equal to minus P by V. And from here, when we get dP by dV, and that is going to be equal to gamma PV to the power gamma minus 1 upon minus gamma PV to the power gamma minus 1 upon V to the power gamma. So this is minus gamma P by V. So dP by dV for an isotherm, dP by dV for an adiabatic is equal to gamma times dP by dV for an isotherm. All right. So when we draw a PV diagram, okay, when we draw a PV diagram, and let us say this is an isotherm. All right. Let us say this is an isotherm. So in that case, this is going to be the slope, right? This is going to be the slope of the tangent, right? This is going to be the slope of the tangent of an isotherm system, right? This is an isotherm, and this is going to be the slope. Now, the slope of an adiabat is gamma times the slope of this. So the slope is going to be something like this. So from here, you can get that adiabat is going to be something like this. All right. So keep in mind, whenever you have an isothermal system and an adiabatic system. So an isotherm is this, and an adiabat is this. Okay, keep this in mind. All right, keep this in mind. Isotherm, adiabat. All right, this is how it goes, right? So now over here, you can see as well, this is an isotherm and this is an adiabat. All right, so this is my system. This is my Carnot cycle. This cycle is known as the Carnot cycle. Okay, now in an isothermal system, temperature is constant. All right, and in an isothermal expansion, work goes out, right? And okay, there would be some heat exchange. All right, some heat exchange. So in an isothermal system, when temperature is increasing, heat is being transferred to the system, right? Heat is being transferred to the system. All right, then in the adiabatic system, there is no heat transfer, but some work can be definitely done. So that work is again, since expansion, so work output. Then in an isothermal system again, heat here, heat would be released, right? Heat would be released because the it is being compressed and work is going to be done on the system. So it is going to be WCD. And finally, the adiabatic system over here, the work is going to be done on the system for WDA, and there is not going to be any type of heat exchange, right? So this is going to be there for a Carnot cycle, right? This is going to be there for a Carnot cycle. Yeah. So when we talk about a Carnot cycle in general, so keep this in mind, for Carnot cycle A, B, C, D. In this A, B, C, D, work done, the net work done would be work done by the Carnot cycle, would be work out minus work in. So work out is WAB plus WBC, and work in is going to be WCD minus WD. All right. So this is work that is going out, and this is work that is going in. All right. Now, this is WAB plus WBC is going to be greater than WCD plus WDA. Therefore, the work is going to be done by the system. So this Carnot engine is going to produce mechanical work. All right. And heat transferred to the system. Heat transferred to the system is going to be heat in minus heat out. So that is QAB minus QCD. This is the entire heat that has been given to the system. All right. Now let's go back to our actual system that we talked about, and let's see how it actually works. So first of all, in the first step, what happens? The gas, this gas, it is going to absorb heat. It is going to absorb heat isothermally. All right. It is going to absorb heat from the high temperature reservoir isothermally. All right. So over here, it is going to get heat. So now the heat that is it absorbs from from a high temperature reservoir, we are going to call it as QH. All right, we are going to call it as QH. Then, as it absorbs this heat, it is definitely going to do some work. All right, it is going to do some work. Okay, in the isothermal system. Okay, now further, when as I told you that A to B is isothermal, then B to C is adiabatic expansion. So further, no heat transfer is taking place. This heat transfer has stopped, but still there is going to be work done by the system. All right, there is going to be work done by the system. All right, so this is going to be B to C adiabatic compression, adiabatic expansion. Then from C to D, it is isothermal expansion. So now what will happen? Now some work will be done on the system. And as this work is done on the system, it will lose some of its heat to the lower temperature reservoir. We'll be calling this heat as QL. Okay, we'll be calling as this heat as QL. And finally, D to A, to come back to its initial state, it is going to we are going to perform some more work on it adiabatically. So we will not allow heat transfer here, but work is going to be done. All right. So throughout the process, throughout this cycle, the net work done, we'll call it as W. So this entire system, what we can reduce this system, we can reduce it to, this is my system. This is my high temperature reservoir. And this is my low temperature reservoir. All right. So this system I can reduce to something like this. This is my final system. All right. This is what is taking place in a Carnot cycle. All right. The high temperature reservoir is maintained at a temperature of TH. The low temperature reservoir is maintained at a temperature of TL. All right. So by energy balance, we can say that heat transferred from the high temperature reservoir is equal to W plus QL. Okay, this is by energy balance. And now this is actually in accordance with the second law. See, all the heat transferred to the system cannot be converted into work. Some of it gets dissipated. All right. So this is the heat that is dissipated. This is the heat that is lost. The rest of it has got converted. Okay. So now from here, we come to the efficiency of a Carnot engine. All right. Efficiency of a Carnot engine. So in general, efficiency is basically output upon input. All right. So what is the output? What is the main purpose of a Carnot engine? We discussed about a thermodynamic heat engine. Thermodynamic heat engine produces mechanical work from heat. So work that is coming out, that is my output of the Carnot engine, right? And what is the input? The heat that is it is absorbing. So it is going to be QH. This is the efficiency of a Carnot cycle. All right, this is the efficiency of a Carnot engine. Okay, and from energy balance, we have QH is equal to W plus QL. So from here, we get W is equal to QH minus QL. So we get neta is equal to QH minus QL by QH, which can be written as 1 minus QL by QH. Okay. So this is my Carnot efficiency of Carnot cycle. For an ideal Carnot engine, considering all these processes that are taking place, we'll have QL by QH is equal to temperature of the low temperature reservoir on temperature of the high temperature reservoir. All right. We can easily derive this by using the equation of states for uh, all these processes. So we'll not just go to that. All right. So this is what you get. So finally, neta max, that is neta for Carnot engine, is equal to 1 minus TL by TH. Okay. And in general, the efficiency of any engine, any thermodynamic heat engine is W by QH or 1 minus QL by QH. So for a Carnot engine, remember, for a Carnot engine, 1 minus QL by QH is equal to 1 minus TL by TH. All right. And for any general engine, 1 minus QL by QH in general, 1 minus QL by QH, which is my efficiency, would be less than 1 minus TL by TH. Okay. Keep this in mind. Okay. So now we move on to a problem. From a reservoir at 600 Kelvin, 1000 joules of heat is transferred to an engine. So this is a high temperature reservoir. So this is my higher temperature, TH. 1000 joules of heat is transferred to an engine that operates on the Carnot cycle. The engine rejects heat to a reservoir at 300 Kelvin. Determine the thermal efficiency of the cycle and work done by the engine. So I'll draw this. This is my high temperature reservoir. This is my system. And this is my low temperature reservoir. Okay. High temperature is given to be 600 Kelvin. Lower temperature is given to be 300 Kelvin. Right? And heat that is absorbed is QH. Work done is W. Heat lost is QL. Right? So first equation that we can make is the energy balance equation. That is QH is equal to W plus QL. All right. Then they have given 1000 joules of heat is transferred to an engine that operates on the Carnot cycle. So 1000 joules of heat, that is QH, is given to be 1000. All right. QH is given to be 1000 joules. Now, efficiency of the Carnot engine is given by 1 minus QL by QH, which is 1 minus TL by TH, which is 1 minus 300 by 600, which is equal to 0.5. Therefore, the efficiency of this engine is 50%. 50% is the efficiency of the Carnot engine. All right. Then the second thing they are saying that determine the work done by the engine, and we'll also determine the heat that it rejects. All right. So now we know that neta, neta is equal to work done upon heat transfer, right? So neta we have calculated to be 0.5. So W is going to be 0.5 into QH. QH is 1000 joules. Therefore, work done is going to be 500 joules. All right. And at the same time, using energy balance equation, we are going to say QL is equal to QH minus W. That is 1000 minus W, which is again 500 joules. All right. So 1000 joules of energy is transferred to the system. 500 joules is extracted from it, and 500 joules is dissipated, which makes the efficiency to be 50%. All right. So hope this part is clear.